Good morning, sir. Respected sir. We are a group of four students presenting our control system activity. Our topic is a root locus using MATLAB and analysis of system stability. Our group members is a Kaveri, me, Sairaj Nikam, Sarthak Pawar. Root locus is a graphical method used to see how system pools move when gain changes. In control system, pool position decides the system stability. If poles are a left plane, system is stable. If poles move in a right plane, system is become unstable. Our objective of our project uh, to understand root locus concept, to plot root locus using MATLAB, to observe poles movement when gain variation, to analyze damping ratio, natural frequency, and system stability. Thank you.
Hello. Characteristics equation and closed loop system. Standard unity feedback is 1 plus k into j of s and h of s is equal to 0. G of s, h of s is open loop transfer function. K is system gain varied from 0 to infinity. Root locus poles of roots of 1 plus k into j of s, h of s is equal to 0 in the s plane. Rules for sketching root locus. Branches number is equal to number of open loop poles. Starts or n locus starts at open poles, k is equal to 0, and end at the open loop zeros, k is equal to infinity. It starts from 0 and end at the infinity. Real axis segment lies on locus if total of poles plus 0 to the right is odd. Asymptotes 2q plus 1 into 180 upon n minus m. N is a poles and m is a zeros. Breaking point. Solve decay upon ds is equal to 0. Stability. System stable if all branches lies in left half S plane for given k. Stability analysis using root locus. There is a chart of the stability analysis. Region of k, poles, location and system response. If the k is less than k marginal, all poles in left half pole and system is stable. If the k is equal to k marginal, then poles on JW axis and system is marginally stable, sustained oscillations. And if the k is greater than k marginal, then the poles in right hand side and the 1 is equal to the 1 and system is unstable. Damping. Use straight lines closer to the JW axis, lower or more oscillatory. Settling time is approximate 4 upon rho, where real part of the dominant pole. Thank you.
So, hello everyone. In this experiment, I have implemented locus analysis using MATLAB. The aim is to study pole movement, system stability, and effect of gain of system response. So there is a step one, define transfer function. We get the first I define the transfer function of the system. This responds the third order system. First, one divided by six s cube plus six s square plus 11s plus 6. Using f of t, using f of t transfer function, MATLAB create the system model. Next, step 2. This is the equation 1 upon s raised to 3 plus s square 6s s square plus 11s plus 6. So next step to root locus plot. In this next I plot the root locus using R locus. This graph shows the how system poles move in the S plane to as the gain varies. Next this is used root locus plot. Next step 3 system stability. I find the open loop poles using poles using this using this poles function. If all poles are in the left half of plane, the system is stable. Next section select gain using RF R locus selection of gain. Here I select the gain. When I select the gain in the root locus plot, MATLAB gives the gain value and corresponding closed loop poles. Next is the step. This is the gain. Select the gain. Next, closed loop stability. Uh, in closed loop, I check the whether the closed loop system is stable or by varying pole location. This and next step 8 step response figure step CL less this graph shows the time response of the system. From this we can observe overshoot oscillation and system time. Next step 8 gain variation. In this we select the gain first gain value is 1, second gain value is 5, second third gain value is 10, and the last one is gain 4 is 20. Here I will I vary the gain value to study the steady state behavior for I is equal to 1 slash length k value. I use a loop next last is the I use a loop to apply the difference gain value and plot the response. So when we run the program, open loop transfer function parameters are so this is the root locus imaginary axis and real axis. So this is the response where when the vary the gain if k gain vary the gain. Next
output of our MATLAB program, that is the root locus. This is the value of k. K is equal to 1, k is equal to 5, k is equal to 10, and k is equal to 20. It is put initially. So run the program. It is the waveform of our root locus, and the given graph represent a detailed analysis of system stability and dynamic performance using the root locus technique along with the step response evaluation of different gain values. The root locus plot provide a graphical representation of how the location of graph closed loop pole change in the S plane. As the system gain k varies from 0 to infinity. Initially, all the poles are located on the left side of the axis, uh, which indicate that the system is stable and exhibit a non-oscillatory response. As the gain increases, these poles begin to move along a specific path defined by the root locus branches. With the further increase in gain, the pole approach the imaginary axis, which result is reduced damping and the one-set oscillationary behavior. When the pole move into a complex plane, the system become undermap, leading to noticeable oscillation in a output response. This two graph is there. One is amplitude versus time, and second is also step response for different gain values. The step response plot further illustrate the practical effect of varying gain on the system performance for a low gain value such as k is equal to 1. The system response is slow and stable with no oscillation, but it suffer poor responsiveness as the gain response to k is equal to 5. The system becomes faster and the rise time decrease through a small amount of overshoot begins to appear. When the gain is further increases to k, like this all is the gain value. This all is the gain value. Uh, a very high gain values such as K20. K20, the system exhibits the large oscillation and excessive overshoot, making it nearly unstable and unsuitable for practical oscillations. In the constraint, the step response for the gain value k is equal to 7.3366 demonstrate an optimal balance between speed and stability. Now we change the value of gains 20 to 30, 10 to 15, 5 to 10, and 1 to 5. This also we have to change. Now check in 10 and 5. So now run the program. Here is the graph between real axis and imaginary axis. So the value of output in step response for different gain values are changed 5, 10, 15 and 30. So as we see the step response value is also changed, k is equal to 1.102. So now conclusion, overall the analysis confirmed that the system performance is highly sensitive to the gain value, which increases the gain improves the speed of response. It simultaneously reduces system stability and increase the risk of oscillations and instability. Therefore, a proper compromise must be achieved by selecting an optimal gain that ensure both good and dynamic performance of stable operation. Thank you.